Welcome to part 2 of Green's theorem. Let's start by reviewing Green's theorem and then we'll look at some additional examples. If C is a simply connected piecewise smooth curve with a counterclockwise orientation in a plane region R, and the components of our vector field f have continuous first-order partial derivatives, then the line integral of f dotted with dr, or the line integral written in differential form, is equal to the double integral over the region R of the partial derivative of g with respect to x minus the partial derivative of f with respect to y dA. So this states a relationship between a line integral and a double integral when the curve C is the boundary of the region R. So if the conditions of Green's theorem are met, many times it's going to be easier to evaluate this double integral here rather than the line integral. So let's go ahead and take a look at our examples. So we want to evaluate the line integral where C is given below transverse counterclockwise. Since all of the conditions for Green's theorem have been met, let's go ahead and rewrite this line integral as a double integral over the region R. This line integral here could be written in differential form as y cubed dx plus 6xy squared dy. And some textbooks like to use this notation instead. Either way, we can rewrite this as a double integral over the region R, where the integrand is the partial derivative of g with respect to x minus the partial derivative of f with respect to y, where little f is equal to y cubed and little g is equal to 6xy squared. So the partial of g with respect to x would be 6y squared, and the partial of f with respect to y would be 3y squared. And now we need to decide the order of integration, whether we want to integrate with respect to y first and then x, or x and then y. And also these are like terms, so we'd have 3y squared. Let's go to integrate with respect to y first and then x. The reason I'm choosing this order is because I recognize the equation of this upper curve as y equals the square root of x. So limits of integration for y would be from 0 up to the square root of x. And the limits of integration for x would be from 0 to 4. So first integrate with respect to y, that's going to give us 3 times y to the third over 3, or just y to the third. Well, the square root of x is the same as x to the 1/2. So we sub in x to the 1/2 and raise it to the third power, we'll have x to the 3/2. And then we sub in 0, we'll have 0. Integrating with respect to x, we'll have 2/5 x to the 5/2. Well, when x is 4, we'll have the square root of 4 raised to the 5th power. It's going to be 2 to the 5th, or 32. And 32 times 2/5 would be 64/5. And of course, when x is 0, we'd have 0. So this is the value of our double integral, which is the same as the value of the line integral, with the curve consisting of curve 1, curve 2, and curve 3, as we see here, oriented counterclockwise. Let's go and take a look at another example. Here we have the same type of problem. We want to evaluate the line integral on the path of C, consisting of curve 1, curve 2, curve 3, and curve 4. So it is piecewise smooth, and it is transverse counterclockwise. So we can go ahead and apply Green's theorem to rewrite this line integral as a double integral over the region R. And by looking at this region, it's probably going to be easier to evaluate this double integral in polar form. But let's first go ahead and set this up. So this will be equal to the double integral over the region R of the partial derivative of g with respect to x. Well, here's g. So this would be 8x and this would be 0. So we'd have 8x minus the partial derivative of f with respect to y. This would be 0 and this would be 2x. So we're going to have a double integral of 6x differential a. Now we're going to convert differential a to r dr d theta in polar form. So 6x would be 6 times r cosine theta. We have an extra factor of r and then dr d theta. So for limits of integration for r, it'd be from 1 to 3. And then for theta, since we're only in the first quadrant, it'd be from 0 to pi over 2. So we're going to have 6r squared cosine theta dr d theta. Let's go ahead and evaluate this on the next page. Integrating with respect to r, we're going to have 6 times r cubed over 3. That'll be 2 r cubed cosine theta when r is equal to 3, we're going to have 27 times 2, that's 54 cosine theta, minus when r is 1, we'll have 2 cosine theta, which gives us 52 cosine theta. And the antiderivative of cosine theta is sine theta, so we'll have 52 sine theta. And the sine of pi over 2 is equal to 1, and the sine of 0 is equal to 0, so we have a value of 52. And we'll stop here for this video. So far, all of our examples, we've rewritten line integrals as double integrals. In the next video, we'll take a look at an application of area where itself will divide a double integral over a region R as a line integral, so we'll use this theorem in the opposite direction. I hope you found these examples helpful. Thank you for watching.